We're going to talk about exponential and logarithmic functions. Let's go ahead and start with exponential functions. In a nutshell, a function is an exponential function if the variable shows up in the power. So this is an example of an exponential function, 2 to the x. If we were to do some evaluating, we have x and f of x, which is 2 to the x. We can put in things like 0, which return a 1, or 1, 2 to the first is 2, and so on, 2 squared. So I'm just changing that power. And then 3, so we get big in a hurry, 2 cubed is 8. If I put some negatives in here as an input, negative 1 reciprocates that base 2. So 2 to the negative 1 is 1/2. We put negative 2 in just so you can get a little bit of a pattern. 2 to the negative 2 would be 1 over 2 squared, or 1/4. So as I graph this one, I can see that I have positive and negative x values as inputs, but only positive values for outputs. So if we take a look at what we've got, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, I went as high as 8, didn't I? I can go ahead and create this graph. So 1 and then 2, 3, let's see, 2 squared gave me 4, which is here. 3 squared gave me 8, which was all the way here. And then my negatives. I had a half and then a quarter, and I would continue to get smaller from there. Okay, let's connect the dots. And what we end up with is this exponential curve. Exponential behavior means that something is growing fairly steadily at first, but then it takes off really, really quickly. So it has this high rate of increase. So something that's growing rapidly, like a bacteria population or something like that, would have exponential growth. So that's the exponential function. We can also do transformations of this exponential function by changing what we have up there in the power. So for example, f of x is 2 to the x plus 3. Well, just like our quadratics, our transformations act in the same way. There's my parent function. I'm going to add a 3 to all of the outputs. So this is a vertical shift up by 3. So I'm just going to take this function here, and every point I see is going to move up 3. So this one, 1, 2, 3, goes here. This one that was at 2 is now at 5. 2, 3, 4, 5. This one that was at 4 is now at 7. 4, 5, 6, 7, and so on. So I end up with a graph that looks like this. Is that about what it should look like? Maybe not perfect, but you can see how I've just taken my graph and I've moved everybody up by 3 units. So all of our transformations happen in exactly the same way. We also want to be able to work with these functions and evaluate them. So I've done a base 2. We also have what we call the natural base. The natural base is base e. And e is, and actually I can just put it in my calculator here, we use e as the natural base because it's used for continuous growth, which would be something like I mentioned the bacteria population growing, or something that was decaying like radioactive decay, things that are organic in nature. Okay, so e. On your calculator, move this up, you'll find e right here on this button. It says ln, but the second value is e. So if I type that in, so I go second e to the x, I get e to the something. It says e to the what? We'll just put e to the first in. And that gives me the value of e. It's an irrational number, and it's approximately 2.718. And it goes on without a pattern and without end because it's irrational. But it's just a number between 2 and 3. So when we start evaluating, like we do, oh, not e, I want e, say, squared. I'm just going to take this number and square it, but I can do that with a calculator. So when I do e squared, I'm just going to go e to the second power. And that would be 7 point, if I were to round it, 7.39 maybe. So we can work with that base e, 7.39. Well, we use exponential functions, particularly when we are working on things like interest problems. So you're going to see some interest problems. That's one great example of exponential growth. So exponential growth. And with these interest problems, we're going to be specifically looking at compound interest. So I'm going to go ahead and give you at least one version of the compound interest formula, and it looks like this. A is equal to P 1 plus R over N all to the N T. Different books will have different versions of this. So your book might even have a slightly different version of this, but even if it does, you can use this formula and you'll get to the same answer. We want to identify what all of these pieces are. A is the value in the account, so this is the account value. P is the principal amount, which would be your initial investment or loan. R is the interest rate as a decimal. N is the number of compoundings. Number of compoundings per year. We'll see some examples of that. 4 is a very common one if it's compounded quarterly, or 12 if it's compounded monthly. N shows up again in our formula, and then T is the time in years. Time in years. Okay, so you want to be able to work with this formula or whatever version of it you're working on. Let me give myself some more paper and we'll look at an example. Let's say that you invest $1,000. So example, you invest $1,000 at 8% annual interest. With interest compounded quarterly. Compounded quarterly. Compounded means that they're going to calculate how much interest you've gotten quarterly. They're going to calculate how much interest you've gotten after a quarter, which would be 3 months. And then they're going to add that back into your account, so the next time you get interest on your $1,000 plus the interest that you earned. Well, the nice thing is that you can just use the formula. So P1 plus R over N all to the N T. I'm going to identify all of our pieces. I'm investing $1,000. So my initial amount, P, is $1,000. 8%, I want R, which is 8%, but I want it as a decimal, so that's 0.08. Compounded quarterly, see, so I've got P, I've got R. Quarterly is, I didn't spell that right, did I? So quarterly is the number of compoundings I have, which tells me that I've got 4 compoundings per year. So N is equal to 4. So I've got everything covered except for T, and T is going to be covered in the statement of the question. Let's see, so how much is the account worth after 10 years? Okay, so if we put everything in, I don't know what the account is worth, so I'm going to leave A as my unknown. A is equal to P, which is 1,000. 1 plus R, that 8%, we wrote as a decimal 0.08, divided by 4 compoundings per year. Notice with that annual interest, you don't get 8% every quarter, you get 1/4 of 8%. So that's why the formula looks the way it does. N is 4, and then T is 10. I'm going to type this into my calculator. You want to be really careful that your exponent is the 4 and the 10 together. I typically go ahead and just compute this and write that as 40 so I don't accidentally leave the 4 or the 10 out of my exponent. I'm going to go ahead and put this into my calculator. As I put this into my calculator, turn it on first, I end up with 1,000. 1 plus 0.08 divided by 4, all to the, so I'm going to use my caret key, all to the 40. If you were going to type in the 4 and the 10, you should, unless your calculator puts the number up there in the power, use parentheses 4 times 10. So you can do that, but just make sure that you've got everything in there how you want it. Okay, so oh my gosh, look, we more than doubled our account value. And our account, this is money, so I'm going to round to the hundredths, is 2208 and 4 cents. We also have something called continuous compounding. So we want to do an example with continuous compounding. So next example is with continuous compounding. I'm actually going to do the same example, continuous compounding. With continuous compounding, we're going to use that base e, and our formula becomes this. A, so the same account, equals P, which is my principal, e to the RT. I'm not going to derive this for you, but what happens is when we let the number of compoundings get really, 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 really large, we end up with this value right here becoming e. It's actually kind of a cool derivation, but I'm not going to do that here. My r represents the same thing, and my t represents the same thing. Now I'm going to do a compound example with interest, even though this formula really makes a lot more sense if you're doing something like bacteria growth or something that actually does grow continuously, which would be something more in nature. But I'm going to go ahead and do this example with continuous compounding. So we're going to go ahead and leave our initial investment at $1,000. We're going to leave our interest rate at 0.08, and we're going to have quarterly compounding, which means that n is equal to 4. So if I put, not quarterly compounding, continuous compounding, but we are going to say that we're going to invest this for 10 years, so t is equal to 10. So to find the amount in this account, A is equal to P, which is 1,000, E to the RT, so 0.08 times 10 goes up in the power. So you can go ahead and put this in parentheses, or if your calculator puts things up as a superscript, you can just make sure that both of those show up as a superscript. So in the calculator, I'm going to type this one now. So 1,000, and I'm going to go ahead and grab E by going to the ln key, so second ln to get e to the 0.08 times 10. If your values don't show up in the exponent there, then you should put parentheses. So you should do parentheses 0.08 times 10, close parentheses. And we get just a little bit more with that continuous compounding. We were getting 2208. Now we're getting about, what, $17 more at $22.25. So now the value in that account is $2,225.54.